the first thing I wanted to say, see if I can remember everything, is that the homework is posted on the website. Yeah, I believe it's due, we can check, but I believe it's due not this Friday, but the next Friday. Does that sound right to everybody? So, yeah. So it's going to be due a week from this Friday. So make sure you guys take a look at that. The due 3 days after that, I think, according to the sorry, due a little while after that. That's going to be 3 days after the homework 2 due date, so substantially later is the due date for milestone 1. Okay, so we also posted on the course website a description of what we're expecting for the first milestone of the course project. We're trying something a bit different this year in that we're going to be allowing for essentially 3 different options for the project. In the past, it was always kind of the same option, which was you're supposed to be kind of thinking of a novel approach to solving a particular optimization problem, either practically or theoretically, typically motivated from some of your own research. That's hard for some people to do, obviously. Not everybody's research is aligned with optimization. It's kind of a lot to ask, especially with a class size this big. I think there's going to be quite a bit of diversity. So we actually introduced 2 other options, which are described in kind of better detail than what I'll give you now on the course website. But just to summarize them, one is an implementation project, essentially. Take a problem you care about. Think about all the algorithms from the course that are applicable to that problem, perhaps a few other variants that we didn't cover as well. Implement them programmatically and do some very thorough comparisons, perhaps in let's say in a regime or a situation which is not quite considered in the literature very much or something like that. So it'll be mostly an implementation project. And for this type of project, we really encourage you to kind of make the result of your project open source eventually, like put it on GitHub. So that's one option other than kind of the first one. The second one is to pick a topic again that you think you're interested in and just do a very thorough literature review of what is known about that optimization problem from a theoretical point of view. So, read 5 or 6 papers, figure out kind of all that's known about it, and summarize that in your final project. So those 2 options require obviously much less novelty than the first option, which is to try to design a new algorithm or adapt an algorithm to solve a new problem or something along those lines. But yeah, so the way it'll work is that you'll form teams of 3 preferably. You'll choose one of these options, propose something by the first milestone, write something short. I think we only ask for 2 to 3 pages. Then we'll match every project team with the TA as their mentor, and that TA will give you feedback as to whether we think you're on course for the project. Okay, so details on the website for the homework and the project. The next thing I wanted to discuss was about scribes really quickly. If you're on the wait list, please do not sign up for scribing. Obviously, that's taking a spot away from somebody who's in the class, and you may not get in the class, and then that wouldn't have done anything, but it would have done something for somebody who's in the class. So remember, we're using the scribes as like if your grade is on the boundary at the end, then we'll push you up if you did a scribe. So don't sign up for scribing, please, if you're on the wait list. Leave that to the people who are in the course at this point. What else did I want to announce? Oh, the quiz. So the quiz is, people have been noticing that there's a bug and somehow that it looks like it's due at 4 a.m. rather than midnight. That happens on sub-browsers. I don't know why it happens. And we're going to keep setting it to midnight. That's the deadline internally. For some reason, it shows up as 4 a.m. for some people. Don't get confused by that. Please just remember that it's due at midnight. We've contacted the folks who run the quiz system, but I don't know if they'll fix it anytime soon. So just remember that it's due at midnight, not much later. I had other announcements. Okay, yeah, so another announcement is that I'm actually not going to be here on Monday. I have to travel for a workshop, so there's going to be a guest lecture. It's a shame because I think Monday's lecture is a really fun one, but I'll secure an excellent guest lecturer for Monday's class. I think that was all the announcements I wanted to make. Any questions before we jump into the lecture? Okay. So last time, we still have a bit to finish from last time on the lecture on convex functions and sets. So I can't actually remember what I said. I didn't check the video. I guess I could have checked the video, but I didn't. But I'm pretty sure I misspoke when I discussed converses of these two theorems we learned, separating hyperplane theorem and supporting hyperplane theorem. So I think I probably said something like there are converses to these theorems, and they require some kind of assumptions that are, separate from what you see here. And I may have said that there's a converse to the separating hyperplane theorem that says that if you have two disjoint sets, if you have something like a separating hyperplane between two sets and one is open and one is closed, then they must be convex. So that's just completely erroneous. I think I may have said that. Obviously that's false because here are two sets. They have a separating hyperplane between them. I could make them both open, in fact. They're definitely not convex. So what I meant to say as a converse to this theorem is that if you have if you have two convex sets, I can just write it so I don't continue to confuse you. Two convex sets. Let's say one open, one closed. And there exists a separating hyperplane. That implies that they're disjoint. That is a converse. Okay, perhaps I don't think it's the most interesting converse. I think it's kind of intuitively obvious. There's another converse that is, I think, more interesting to the supporting hyperplane theorem. So the supporting hyperplane theorem has the following converse. If we have a set that's closed and it has a non-empty interior, and it has a supporting hyperplane, there exists a supporting hyperplane at every boundary point. Then this implies that it's convex. That one I think is much more interesting. So just wanted to clarify these converses. Okay. I think I gave a reference. You can see some details in this chapter of Boyd and Vandenberg. So last time we proceeded to talk about convex sets and functions, and we got all the way to, basically we got all the way to composition rules, and then we stopped. So we didn't talk about operations that preserve convexity that have to do with composition for functions. So one very useful composition rule to know and to invoke whenever you can is that if you have a convex function and you compose it with an affine function, so if I have, let's say, f, and I look at the function f of ax plus b, where a is a matrix and b is a vector, and I call that function g, then that's always convex. So this is a super useful composition rule because let's say for the biggest use case of this one is that it avoids you having to use the chain rule. So if you knew that f was differentiable, or maybe twice differentiable, and you wanted to check whether or not this composition was convex, you would take two derivatives, right? That would require you to remember what the chain rule was, essentially, and sometimes can be more complicated than you want it to be. Suppose if we have several compositions of affine functions, or if we combine this with one of these rules, and it's just a complicated calculation, you can just immediately say that, well, if I have a convex function and I compose it with an affine function, it is going to be convex. More general composition rules are tricky. So it's not generally the case that just composing two convex functions gives you something convex. But if you know that the outer function in the composition has some kind of monotonicity property, then you can get a convexity preserving transformation. So here are 4 rules I wrote down. In fact, there's just really 2 rules, and then to get the concave variance, you can just think about, again, flipping the sign. But we can just talk about, for example, we can just talk about the first one, for example. If we have the function, let's say h composed with g, and g goes from Rn to R, h goes from R to R, and so the composition f goes from Rn to R, then this composition f is convex if this outer function h is both convex and it's non-decreasing, and the inner function g is convex. Okay, so the key thing here is this non-decreasing property. Without this, this would not be true. This composing 2 convex functions, as I said, would not necessarily give you a convex function. So a variant of this is that if g is concave and h is convex and non-increasing, then the composition f is convex. Okay, and we essentially can, like I said, derive the other 2 rules just by thinking about flipping signs. So the way that you remember these, other than just coming back to the slide, is to think about just looking at what the chain rule does in the case when n is 1. I think this is a very useful way to remember them. So suppose that I just had f is h composed with g. Every function here is real valued and takes a real argument. So f double prime, the second derivative, right, just by the chain rule, we can work it out. So f of x is h of g of x. Right, so f prime of x is going to be, let's actually just jump to, right, just using the chain rule, it's h prime of g of x times g prime of x. And if I look at the second derivative, I have to both apply the chain rule and think about the product rule. Right, I get h double prime of g of x. So I'm going to differentiate this term first, multiply by this. I get a g prime of x from the chain rule, and I already have a g prime of x, so I get a g prime of x squared. And now the second part of the product rule, right? I'll leave this alone, I'll differentiate that. I just get h prime of g of x times g double prime of x. Okay, so now we can think about this expression, and we can actually derive all of the rules I wrote down on the slide from just this one expression. So let's see. If, let's suppose g is convex, then this thing is going to be positive. Right? When g is convex, this is going to be positive if g has 2 derivatives. And if h is convex, this is going to be positive. So that's good. But this whole thing is not going to be positive necessarily unless we figure out the sign of this. So this is always going to be positive. We don't have to worry about it. But this is where the monotonicity properties of h come into play. If h is a increasing function, then this will be positive as well. So we have the product of 2 positive things. This is positive. That's always positive. F double prime is always positive. That's the way we derive the first rule. If we look at the second rule as an example, if h is convex, okay, this is positive. That's always positive. Now, if g is concave, that's negative. But if h is decreasing, that's also negative. So their product is going to be positive. F double prime is going to be positive. The whole thing is convex again. And you can actually check the latter of the 2 rules here in the same way. So this composition rule does not assume differentiability. It does not assume 2 derivatives. It actually holds, when g is defined on Rn. But the way to remember at least all of the different parts is to just think about this simple case. Write out the chain rule for the second derivative of f. Okay, so that's a general composition rule. There's a more general version of this rule which has h itself being, which has g, which has the image of g being like rk rather than r. Its range space not being r but rk. So h not being a function on r but actually on rk. That's an even more general case than this. everything we have here is the same as we had in the previous slide, except for these monotonicity properties we require on H have to be applied component-wise. Okay, so it's the same set of rules, except for, as an example, we have to have H being convex and then non-decreasing in every argument rather than just being non-decreasing, because now it's a function on Rk. So if G and H are convex and H is non-decreasing in every argument, then the resulting function is convex. So again, the way to remember all of these rules is really just from this simple case. And then you'll kind of be able to always derive them if you don't have these slides handy, let's say. Okay, an example of that, actually it's not quite an example of the complicated composition rules, just affine composition. Something I stated last time and we didn't really go through the proof. I think because we're a bit behind, I won't go through the proof again, but I'll just highlight that this is an example of where invoking the affine composition rule would save us a lot of calculation. So this is called the log-sum-exp function. It's also called softmax. The function is defined as the log of the sum of e to an affine function of x. So ai transpose x plus bi for some vector ai and scalar bi. And it smoothly approximates the maximum. So it's a smooth function. It's actually convex. And it can be viewed as an approximation to the maximum. In fact, we can both upper bound and lower bound the maximum by some constants times this. So how do we show convexity of this function? So the first thing I would do if I was solving this problem is I would actually say, well, this is just this particular function, log of the sum of e to the xi composed with an affine function. Right? If I think about composing this function with matrix ax plus b, I'm getting this function. And I'd rather not have to be worrying about matrices when I'm doing derivatives, because I have to be carrying through things via the chain rule. It's just going to complicate my calculations. I'll just say that if I can prove convexity of this, then by the affine composition rule, this will be convex as well. Save me some time. And to prove convexity of this function, one way is to look at the second derivative, or its Hessian, because it's a multivariate function. And it turns out that in this case, its Hessian, we can actually just see directly through calculation that it is positive semi-definite. Okay, we're using a trick from linear algebra where when we look at its Hessian, it's easy to see that its Hessian is diagonally dominant, which means that every diagonal element is bigger than the sum of the absolute values on that row. It's called diagonal dominance. And if you went back to a linear algebra course, hopefully they would have told you that diagonal dominance implies positive semi-definiteness. In strict diagonal dominance, if the diagonal element's actually strictly bigger than everything, than the sum of the absolute entries on that row, then it implies invertibility or positive definiteness. But we just really need, diagonal dominance. It implies positive semi-definiteness. And then from our second derivative characterization, right, the one we learned here, if we have that the Hessian is positive semi-definite everywhere, then it's convex. So that was a way to show convexity of this function. Okay, so without further ado, I now want to jump into second part lecture on optimization. I mean on the kind of some of the basics of convexity. And here we'll talk about optimization problems, try to do a comprehensive look at kind of all the various aspects of optimization problems, how convexity kind of plays a role in various aspects, and introduce a bunch of terminology that we'll use for the rest of the semester. And again, see some of the reviews we have on the website if you're finding that some of the kind of core mathematical concepts are difficult to follow. So last time, which also carried over into this time, we talked about convex sets and functions and essentially some of the key properties and operations that preserve convexity. And so I just had an example here. How might you think about, is this function convex? So it looks like a nasty function, but let's see if we can apply some of the, you know what, since we're short on time, I actually will say, I'll just leave it as a challenge to see if you can figure out this convex, and you come talk to me at the break or after class if you're finding that it's difficult. Hint, hint, this is convex. It's just it looks particularly nasty, but if you apply some of the rules we learned for operations that preserve convexity, you can reduce this to base examples that you know are convex plus a bunch of transformations. So if I gave you this before the last lecture, I think you would look at me perplexed, but hopefully now, at least with some practice, you can kind of tackle what looks like complicated expressions. So today's outline, we'll talk about optimization terminology, properties, in particular, a condition for what we call first order optimality that has to do with the gradient of the criterion. And then we'll look at a bunch of equivalent transformations of optimization problems. So we've covered this before, but I'll just do it again for completeness. In general, an optimization problem, we also call it sometimes a program. It takes this form. We write it as the minimum of some criterion function f. We also call this an objective function. Overall points x in a set D, where this D is the intersection of the domains of all of the functions that appear in this problem. Subject to a bunch of conditions, we have inequality conditions. These are called usually inequality constraint functions, gi of x less than or equal to 0. And here I'm actually specifying a convex optimization problem, which means that actually f and gi have to be convex, and this equality constraint has to be linear. Okay, so we have ax equals b. So a bunch of terminology again. F is the criterion of the objective function. These g's are called inequality constraint functions. If we have a point that's in the domain, that's common to all the functions, and it satisfies all the constraints, meaning it satisfies these inequality constraints and it satisfies these equality constraints, then we call it feasible. And the minimum value of f over all feasible points, we call the optimal value, and we write it as f star. That's, if we have, let's say f is the criterion function, then we'll write f star typically as the optimal value of this problem. Right. So why can't I have anything else than linear constraints in a convex optimization problem? I guess we have not gone over that. Linear equality constraints. Why can't I have like a generic convex function set equal to 0? I claim that would actually lead to a kind of a contradiction in the way we've defined the problem. Let's see if somebody can see that.
So a solution set to a base function would be linear.
That's true. I'm looking for a more basic reason, though. I mean, you've invoked a property of convex optimization problems as we've written them here. Yeah.
Function that is both. So suppose you're only using the inequality constraint. So essentially, you'll be having ax less or equal to b and negative ax less or equal to negative b, and a function that is both convex and concave must be affine.
That's right. It's a great answer. So if we have something like this, then we can write this as a pair of constraints. Right? This is equivalent to these two pair of inequality constraints. And now, per what we know about our inequality constraint functions, we're requiring both h and minus h to be convex functions for this to be a convex optimization problem. And the only h that's both that satisfies both h being convex and minus h being convex, or in other words, h being convex and h being concave, is an affine function. So once I've told you that we can only have convex functions that we're comparing to 0 in terms of these inequality constraints, that actually restricts what we use for equality constraints to things of this nature, right? Some affine function equals 0, or ax equals b. Okay, more notation or nomenclature. If we have a point that achieves the optimal value, so f of x is equal to f star, then we call it optimal. We also call it a solution to the optimization problem, or minimizer. An important footnote is that optimization problems, even convex ones, need not have solutions. No one's telling you that actually they have a solution. that's, let's say, finite or in the domain of the function. And a good example of that is, let's just say that my function is e to the minus x. Okay, it's convex. It has domain all of R. Its optimal value, if I were to look at minimizing it, is 0. But I can't find you a single x that achieves that optimal value, right? We say that this problem, minimizing f of x, does not have a solution for that value, for that reason. So there's quite a bit of kind of important work in convex analysis that goes towards proving that certain optimization problems have solutions in the first place. We're not going to be careful about that at all, because it just requires introducing a bunch more geometry and kind of it's a more mathematical take on the subject. Most optimization problems that we'll look at in this class, if not all of them, will have solutions, and we'll just kind of ignore that aspect. But if you're interested in learning more about that, you can come ask me in office hours. The Rockefeller book has a lot of kind of very good material that goes into sufficient conditions for optimization problems to have solutions. Okay, so it's an important footnote. Basically, like I said, everything we're going to do from now on is going to assume that our optimization problems have solutions. But you should remember that that's not necessarily the case in every example. If you have a point that's feasible and the criterion value at that point f of x is, let's say, bounded by f star plus epsilon, then we call this point epsilon suboptimal. Okay, that's the nomenclature we assign to it. And another important piece of nomenclature, if we have a feasible point and we say that, let's say, this inequality constraint function here that we had in our optimization problem, if it's actually equal to 0 at x, then we say that this constraint function is active at the point x. And let's suppose x was actually the solution. We would say that certain constraints are active at the solution if we had, gi of that solution equal to 0, rather than being strictly less than 0. So these are called active constraints. And another one that's important to point out is that, if I ever talk about a convex minimization problem, I can equivalently pose that as a concave maximization problem just by flipping the sign of the criterion and turning the min into a max. Right? So minimizing f of x is the same as maximizing negative f of x in terms of the solutions here will be solutions here. Right? The optimal values will just be the negatives of each other. So I will call this a convex problem. If we ever see a problem like this in which f is concave, or rather, sorry, in which the criterion is concave. So here we have minus f being convex, so the criterion is concave. So concave maximization is, we're going to refer to that as convex optimization. We'll just kind of generically call both of these convex optimization problems. Okay. A very important property of convex optimization problems is that their solution set, which is the set of all points that attain the optimal value. We usually write this as capital X opt. That this is actually a convex set. So for convex optimization problems, this is a convex set. Not at all the case for non-convex problems, obviously, right? If I'm minimizing this function, maybe this solution has these two solution set contains these 2 points. It's clearly not convex. So, right. And remember that this can actually be an empty set as well. X opt can be empty. That's a possibility for functions like this one. So the proof of this just follows from the definitions. It's actually very similar in some sense to the proof we did at the end of the first lecture. Basically, you just take 2 solutions. Okay, and you look at any convex combination of them. So tx plus 1 minus ty, if x and t are x and y are solutions. And you check that, well, we didn't actually write this down. You have to first check that that's in the domain. That's common to all the functions. But we know that's true because, the domain's intersection of convex sets, it's convex. So, if I have x and y and d, their convex combination will be in d as well. We have to also check that, it's feasible. So if you take tx plus 1 minus ty, it meets all the constraints. That, again, just follows from convexity now of the functions, let's say, gi, that define the inequality constraints. That's just invoking their definition. And to check that it meets the equality constraints, we're just actually using linearity. So it's very straightforward to check. And finally, we can just look at the criterion value right at tx plus 1 minus ty, because we know it's feasible. And checking the criterion value, we know that it's, again, due to convexity, bounded by tf of x plus 1 minus tf of y. Both of these are equal to f star by assumption, because they're both solutions. And so this whole thing's equal to f star. And if we have a point that has something less than, achieves a criterion value less than or equal to f star, it actually must be equal to f star, right? Because this is the smallest we can make the criterion value. So we've just shown that this is also a solution. Okay. Another key property, and this is one that we'll use often in practice, is that if the criterion is strictly convex, then the solution is unique. Actually, this set only has one element. Or it can also have 0 elements as well. Actually, I should maybe clarify. This function is strictly convex, and it doesn't have a minimizer. So strictly convex just means that the solution is unique if it exists. But again, we're kind of ignoring issues of existence for the most part. So how do we prove this? That's actually the same as this, except for we just look back at the last line, and we say that if x and y are not equal, and t is, let's say, in between 0 and 1, so we have actually two properly different solutions, and we're looking at some convex combination that actually lies strictly between them, then by strict convexity, right, we would get that this is actually strictly less than tf of x plus 1 minus tf of y, and that would be equal to f star. So we'd have proved that their convex combination is strictly less than f star. And that's impossible, because nothing can be better than the smallest we can make the criterion. And so actually, we couldn't have had two properly different solutions, x and y, in the first place. So it's just again, very similar to the proof we did at the start of the first lecture. We're just saying, by contradiction, if we had two different solutions, then somewhere between them, on the line joining them, we would actually beat the criterion value if f was strictly convex. So we could only have had one solution in the first place. Okay, so strict convexity implies uniqueness of the solution. So just maybe working through a lot of these concepts is helpful. It's helpful to see some examples in which we can discuss what they are specifically. We talked about the lasso in the very first lecture as being one of the optimization problems that we'll revisit, because there's a bunch of algorithms that we can apply to it. It provides kind of a nice working ground for a lot of the algorithms we'll discuss. Same with support vector machines. And here I'm writing down what I call the constrained form of the lasso. So last time we saw the penalized form. We looked at the least squares loss plus something like lambda times the L1 penalty of the coefficients. This is the constrained form. So we're actually constraining the least squares loss by the L1 norm of the coefficients being less than or equal to some parameter s. So what we'll see much later is that actually this is in a sense equivalent to the penalized form. This is actually an application of, it's really an application of essentially the KKT conditions in duality that ties these two together. But you probably are familiar with this from maybe just encountering different formulations of problems in the literature where people either write them in constrained form sometime or penalized forms other times. So the lasso, we didn't really give much motivation for it. As I mentioned before, we kind of won't really give much motivation for these types of problems. I'm just hoping that you're already familiar with them. So it's a way in order, it's an optimization problem that'll give us a sparse estimate of some regression coefficients. So we're looking to minimize the squared loss between y and x beta, and this is actually going to invoke sparsity in the solution, this kind of L1 norm constraint. So let's start off by answering some basic questions. Is this a convex problem? Hopefully everybody, that we don't actually need to answer that. We can just say yes, it's convex because, well, there's many ways to look at it actually. This least squares loss we know is convex because it's a quadratic, and if we write it as beta transpose q beta, then that q is x transpose x. It's always positive semi-definite, so this is always convex. Right, we can also think this is just the sum of squares, so we know that function's convex, and I'm composing it with an affine function of beta, so it's still convex. Two ways to look at it. This is a convex function because it's a norm. We know that norms are convex. And I'm comparing it to S, but I could also write this as the L1 norm of beta minus S less than or equal to 0. So S is just a constant here. So that's still a convex function we're comparing to 0. And there are no equality constraints. So it is certainly a convex problem. This is the criterion. The inequality constraint function, as I said already, is for this example, it's just g of beta is equal to the L1 norm of beta minus S in our standard notation for convex problems. The feasible set is the set of all points. Since the domain of this function, of both of these functions, is all of, let's say, Rp in this example, the set of feasible points is actually just a set of betas that satisfy this inequality, which we call the L1 ball of radius S. And now we can proceed to maybe answer a bit more sophisticated questions like, is the solution unique? So let's say n is larger than p here. So let's say x is an n by p matrix. N is bigger than p. And x has linearly independent columns, or has full column rank. How many people think the solution is unique in this case? Raise your hands. I got surprisingly fewer people than I thought I would see. So maybe somebody who rose their hand could explain to me why they think it's unique. So the only condition we know for uniqueness now is strict convexity, right? That's the only thing we know at this point. It's going to imply uniqueness. So the criterion function is y minus x beta and 2 norms squared. And this is equal to beta transpose x beta minus 2 y transpose x beta plus y transpose y. If we expand it out. So to check strict convexity of this function, what would I have to do? Sorry, okay, say it again. Yeah, that's right. Well, that's kind of one step ahead of where I wanted to go, but we could take, for example, a Hessian. Okay, a Hessian is just x transpose x. Okay, these calculations should hopefully all be very comfortable to you. All right, if I take 2 derivatives with respect to beta, this goes away. This just gives me x. Actually, it's 2x transpose x, I guess. But it doesn't really matter. So when is this going to be strictly positive definite? This is going to be strictly positive definite when this matrix is invertible, right? So this is strictly positive definite if and only if x transpose x is invertible. And that's true if and only if x has linearly independent columns. Right? If all my features, which we think about as being the columns of x in the context of the lasso, are linearly independent, we also say that x has full column rank. It's another way of saying it. Then we get strict convexity of this loss, and so the solution is unique. Okay, this would be true even if I didn't have any constraint here, right? In the case when this is called a low-dimensional case in the context of regression, if I have linearly independent features, then regression is well-defined. There's a unique minimizer to this, even without constraints. So we're just kind of saying the same thing now, but for the lasso, in the presence of constraints. So how about in this case, when p is larger than n? So when p is larger than n, there is no way that this matrix can be invertible. Right? It's just not possible. I can't have p things being linearly independent in Rn if p is larger than n. Right? I can't have more than n things being linearly independent. So when p is larger than n, this matrix is not going to be invertible. Another way of saying that is that x is going to have a proper null space. So there'll be some vectors for which x times that vector, say v, is going to be equal to 0, but v will not be, I don't have to have v being equal to 0. And I will not be able to find, you might think, generically a unique solution to this problem. Because, well, we don't have strict convexity, and at this point that's all we know kind of to imply uniqueness. Much later on, after we cover the KKT conditions, I'll perhaps surprise you and tell you that in this case, if we look carefully at the KKT conditions, we can actually see that we really often still get uniqueness in the lasso when p is larger than n. And it's kind of a neat application of just the KKT conditions with some very basic probability theory. And by very often, I mean, as a concrete statement, if x, let's say, has entries that are continuously distributed, so x was random, it has a matrix with random entries, and those entries had just any kind of continuous distribution, then with probability 1 over that distribution, we get a unique solution to this problem, even if p was 1,000,000 and n was 10. So that's a fact that comes really straight from the KKT conditions, combining with a little bit of probability theory. And if we have time, we'll prove that when we talk about the KKT conditions. OK, think about it maybe on your own. How would the answers to all of these questions change if I just changed the criterion? OK, so if I changed it from squared error loss to Huber loss, which some of you might have seen as maybe being a more robust version, a more robust loss function. So the Huber loss basically just takes a quadratic and clips it to be linear outside of some interval. So here the interval is minus delta to delta. It's a function that looks like it's quadratic between minus delta and delta. And then outside of that, it just turns into a linear function smoothly. So if we replace the squared loss with this loss, then it would be a way of maybe being more robust against really large outliers or deviations away from linearity that we find, that we would otherwise be placing a lot of weight on if we looked at just the squared loss. So some people like this a lot, and you might just think, how would the answers to all of these questions change? It's still convex, by the way. OK, another example that we'll walk through, and then maybe we'll take our break, is SVMs. So again, hopefully something you guys have seen before. I'm not going to spend a ton of time motivating it. I'll just say that SVMs are a way to do classification in this formulation in a potentially non-linearly separable setting. So we have data. Suppose I'll write my data points as pluses and minuses for when y is +1 and -1. And suppose we have a setting in which the two classes are not separated by any linear decision boundary in feature space. So this would be my feature space, maybe x1, x2. So the support vector machine is is an optimization problem which defines the decision boundary. So it defines essentially an affine, it defines a hyperplane through this feature space that tries to maximize the margin between the two classes, subject to their allowing there to be some kind of overlap. Okay, so the hyperplane that we're fitting is actually just this one. It's at a point x. It's defined by x transpose beta plus beta 0. Let's say being equal to 0. That'll be the affine space. So in this example, I don't know, visually maybe we'll fit something like this. This will be x transpose beta plus beta 0 equal to 0. That'll be the affine space. And these, it's funny, every time I teach this, I can't remember what Greek letter this is. Is this a psi? I always forget. Is that a xi or something? It is a xi. Yeah, I should really change that. I never can remember what this is. So these c variables or xi variables, they stand for essentially the slack variables. So they are non-zero when we have a point that's on the wrong side of that boundary. Okay, again, hopefully something that you have seen in previous classes. So this allows for some amount of overlap. Okay, we're saying that the label times the essentially the value of x transpose beta plus beta 0 we're allowing it to be bigger than or equal to 1 minus some ci, where ci is something that's actually it's allowed to be positive. So there can be some kind of overlap. I can be a negative label on this side of the boundary, right? That would just mean that this ci here is actually something non-zero. And the criterion essentially tries to minimize the margin between the two classes, which a bit of calculation you can figure out that that's actually 1/1/2 the norm of beta squared. Beta is, again, that's the coefficients we use to define the affine space. Plus, we're going to penalize kind of the overlap. So the sum of the slack variable ci times the tuning parameter c. So another interesting problem, we'll revisit this when we talk about the duality and the KKT conditions, and we'll talk about kind of alternative formulations for this. Maybe we'll we're going to talk about algorithms to this as well throughout. So let's walk through kind of the same set of questions. Is this convex? So yes, this is convex, right? And this is convex. The variables here are beta, beta 0, and c. This is a linear function. This is just a quadratic function, or it's the norm squared. Both ways we can think about it, it's convex. So the criterion is convex. This is comparing a linear function to 0, but I can also write that as minus c being less than or equal to 0. So that's still convex in my variables. And same here, right? This is just a bunch of linear inequality constraints. Linear inequality constraints are always convex. I can just rearrange them to write it as something convex less than or equal to 0. Right? Because linear functions are both convex and concave. I can always rearrange that to fit that form. So check on convexity. We already said what the criterion is. The constraint functions are just negate, minus ci, and also move everything to one side. So you compare everything to 0. It's the function on the left-hand side. Those are the constraint functions. There are no equality constraints. Okay. The feasible set is the set of beta 0, and c that satisfy these inequality constraints. The domain of all the functions is again all of the space, so there's no additional constraints there. Okay, now in coming to a bit more of interesting / challenging questions. Is this triplet unique? Beta, beta 0, c. This is my optimization variable, right? When I kind of concatenate into one big variable. Is it unique? What do you guys think? Well, again, we kind of only really know that we can prove uniqueness from strict convexity. So what do you guys think based on that? Is the criterion strictly convex? It's not, because this is linear, right? In one of my variables. So at this point, we really can't say that the solution is unique. Okay. How about, forget this. This is just a follow-up asking you to answer that if we change the criterion. So I'm actually going to strictly convexify the criterion here. So you should see that it's unique after I do that. This is a more interesting follow-up. What about just beta at the solution? Is that unique? What do you guys think? No. Some people say no. So why do you guys think it's not unique? Or who thinks it is unique? Yeah.
Arguing against uniqueness, if you imagine rotating your data points, then if you imagine your data points having some sort of symmetry, then you can imagine keeping the same data with that, with different betas.
Okay, so you're saying that I'm actually not sure how to rebut that, but because that seems believable as well. But mathematically, we can prove that it's unique just by using strict convexity of this part. So actually, here's why it's not a counterexample. Well, no, actually, let me hold off on saying why that's not a counterexample. I thought I had a rebuttal, but let me prove to you it's unique, and then we can maybe all think about why that's not a counterexample. on our own time. Or if I come with a solution soon, I'll let you guys know. If we just look at the beta component of the criterion, then the dependence is on this, the norm of beta squared. And this function is strictly convex in beta alone. Right? So suppose I had beta, let's say call it and beta naught in C, and I had another proposed solution, which I'll call maybe beta tilde, beta naught tilde in C. I had two solutions, and I'm asking you whether or not this is possible. Beta is not equal to beta tilde. So you can actually just check that if I take a convex combination of these two things, okay, then it'll of course still satisfy all the constraints. That's just convexity. This will be less than or equal to what it was for each of those two things, but this part will be strictly less than what it was. Okay, so the beta component itself cannot be unique. Must be unique. Because if it was not unique, if we had ever something of this form where these two first components were unequal, then we could achieve a contradiction just by looking at strict convexity of that first term. Okay, I think that's probably a good spot to take a break, and we'll come back in a couple minutes. We still have quite a bit to get through, but a lot of it is examples, so hopefully that won't maybe take quite as long. But let's just pick up where we left off. So another key property, I won't repeat it in mathematical detail, but we proved this the first lecture. We've emphasized it so far. Of convex problems is that they can't have somehow like proper local minima. So anything that's locally optimal is automatically globally optimal. Proved that in the first lecture, and again, it just follows really the same as these proofs do, just using convexity. So a very nice and important property of convex problems. Okay, so moving on to some things we can do with convex optimization. And some of this actually will apply beyond convexity, so it's just helpful kind of see a lot of these tricks in one lecture. If we have an optimization problem of this form, I can always recast it as minimize f subject to x being in some set C. This is completely general, this formulation, because I can just collapse all of the feasible points into one set C notationally. So here C is a set of all x for which all of the constraints hold. Okay, and when these functions are convex, this C is a convex set. The feasible set is convex. That follows some things you already know. If I look at the sublevel set of GI, since GI is convex, at level 0, that's a convex set. I'm intersecting a bunch of convex sets by requiring that to happen for all I. I'm intersecting another convex set, which is just a linear space, or this is actually an affine subspace, the set of solutions to a linear equation. So I'm intersecting a bunch of convex sets. It's still convex. So for a convex optimization problem, it's actually completely general to say I want to minimize some function f subject to my variable x being in some convex set C. That encompasses the same range of problems as this does. And going one step further, we can actually always think about unconstrained problems. It's not necessarily a useful formulation, but it's just, again, something to know. We can always think about unconstrained problems if we're willing to let our functions take infinite values, like our criterion function take infinite values, by just rewriting this constraint x being in C as another term in the criterion, f of x plus the indicator function of the set C at the point x. So this is going to be 0 when x is in the set C and infinite otherwise. So it's going to enforce the constraint that x is in the set C. So really, again, unconstrained optimization is also fully general if we are willing to let our criterion function take infinite values. Then we can kind of wrap in constraints via indicator functions. Okay, maybe more practical as a thing to know. This is just, that last one was just so that you you recognize kind of generality in various forms. This is actually a practical thing to know. For a convex problem of this form, which again we know is fully general, if we have a differentiable criterion, so it's not only convex but it has a derivative, then a particular point is optimal, x, let's say a feasible point, so one that's in the set C is optimal if and only if it satisfies the following condition. The inner product of f of x, of the gradient of f of x, with y minus x is always non-negative for all y in the set C. So if we don't have any constraints, let's look at that case first. Let's say C was all of Rn. Then this condition actually reduces to the gradient of f of x being equal to 0. Okay, so let's maybe convince ourselves that that is the case first. So why do you guys think that's true? If I know this condition holds, then I'm claiming this actually implies the gradient is 0. Well, you can check that actually this is going to imply that the gradient is that the inner product of, let's say, f of x with a is going to be, let's say, greater than or equal to 0 for all a. Okay, but if that's true, and let's say I just look at a and minus a, then that implies that the gradient of f of x must have a 0 inner product with all a, right? Just by looking at taking a and minus a in the above equation. And now I can just, for example, take a to be each one of the canonical basis vectors, like 1 then all zeros, then 0 then 1 then all zeros, to find out the gradient itself must be 0. So if I ever have, let's say unconstrained smooth convex optimization, then this is a condition for optimality. The gradient must be 0 at the solution x. If I have constrained smooth convex optimization, then this is a condition for optimality. We call this the first order condition. Its proof is actually very simple. I skipped it. It's something I could have given on the homework. I think it's probably in the Boyd and Vandenberg textbook. And I think it's also intuitive. The way that I remember it is as follows. So suppose I'm at a point x, and I'm thinking about moving to a point y. And I'm looking at, let's say, the vector y minus x. So this is the vector y minus x, points from x to y. Then if I'm at the point x, and if I'm thinking of moving to y, which is also feasible, if the gradient tells me that's a bad idea, which means that the gradient in this direction is positive, inner product of the gradient with this direction is positive, and that's true for every vector y I could move to, then I must be at the minimum, right? Because it's telling you that you're going to only increase the criterion if you try to move to any other feasible point, because the gradient is actually aligned with this direction according to this criterion. That's the way that I would remember it. Okay, and of course, in the let's say in 1D, this condition that the gradient of x is equal to 0 reduces to what you know, which is that f prime of x is equal to 0. You probably learned that in say in high school calculus or something. So this is really just a generalization of things that you know in more complex forms, at least with this condition, all y in C. So we can actually use this unconstrained result to look at minimizers of a quadratic. I'm probably going to skip this example. I think it's really rather basic. It's just telling you that the minimizer of a quadratic is the solution to a linear system. It's kind of hopefully something that you guys should all remember, again, just generalizing from the 1D case. So if I ever want to minimize this quadratic, let's say in the case when q is strictly positive definite, so I have a strictly convex function, then there's a unique solution, and it's minus q inverse times b. In the case when, let's say, q is not strictly positive definite, so it's positive definite, but it's non-invertible, so we say it's singular, then actually there could be no solution, or there could be infinitely many solutions. And this is just a basic kind of application of linear algebra. So if Q is singular and B is not in its column space, then there is no solution to this linear system, right? So that means that there will be no minimizer to this quadratic. And if Q is singular and B is in its column space, then I can find infinitely many solutions to this linear system. So there are actually infinitely many minimizers to this quadratic. Okay, another example of something that we can prove right from this first order optimality is we can prove what we call the Lagrange multiplier condition for equality constrained minimization. So we'll kind of greatly generalize this when we talk about the KKT conditions, so I'm not going to focus on this too much. It really actually follows a very similar logic from what I just did here with you. You can apply first order optimality, so this result, that we have a minimizer for this equality constrained problem if and only if gradient of f at x transpose y minus x is bigger than or equal to 0 for all feasible y, which means that y is such that a times y is equal to b. You can actually just rewrite that, prove this is equivalent to essentially the following condition. The gradient of f of x transpose v must be equal to 0 for all v that are in the null space of A. Okay, and using again, another basic fact in linear algebra, the orthogonal complement of the null space of A is the row space. So if I tell you that something is orthogonal to everything in the null space of A, it must be in the row space of A. So this means that I must be able to write grad f as, let's say, minus A transpose U for some point U, which gives us this condition up here. So I talked through that kind of quickly. It was just an application of a bunch of, hopefully, to you familiar linear algebra that shows that rewriting this condition leads to this condition. Grad f of x plus A transpose U is equal to 0 for some U. So if I have a solution to this problem, that's true if and only if I can solve this nonlinear system of equations, grad f of x plus A transpose U is equal to 0 for some points x and U. It's often called this Lagrange multiplier optimality for this equality constrained problem. And as I said, we'll kind of greatly generalize this and prove a much more general version of this when we talk about the KKT conditions. Okay, I think for the sake of time, I'll just skip this example. It's just invoking another application of first order optimality, but now for a projection problem. I think you get something that's actually fairly natural. It's another thing you can interpret geometrically, but it's again, it's just a straightforward applying this first order optimality condition to the problem of minimizing the squared loss between, let's say, some fixed point in x subject to x being in some c. So this is projecting a point A onto a set C, finding the point in C that's closest to A in Euclidean norm. So when we apply the first order optimality, we get some people call this a variational formula for projection, but it's just an application of first order optimality. Okay, here's something that's a very useful thing to know in a different direction. If we have, let's say, a convex function, and we split up the variables into two blocks, x and y, and maybe we just focus on the constraints that are on y, and that we call that some set C. If we were to partially minimize out over y, then we get a function that's just of x. And remember, we said that that function is convex, provided that C is a convex set, and f is convex in x and y. So this fact implies that we can always take a convex problem that has many variables, let's say minimize away over some variables or partially minimize, and retain a convex problem in the remaining variables. So that's a very useful fact. Here's an example. Let's suppose we had an optimization variable x, and we decompose it into two parts, x1 and x2. Those are two blocks. And we had let's say a convex problem that looked like this: minimize f subject to g1 of x1 being less than or equal to 0, and g2 of x2 being less than or equal to 0. If we minimized out over x2, so it means that we defined, let's say, f tilde at the point x1 to be the smallest we could make f of x1, x2, provided that g2 of x2 is less than or equal to 0. So we try to fix x1 and solve out for x2. And we define this new function f tilde accordingly. Then we get a problem in the end that's only a problem involving x1. And this is still a convex optimization problem. Why? It's because this function f tilde is actually still convex. It's just an application of this fact. Okay, so sometimes we can simplify a problem by maybe analytically or exactly optimizing away some variables. And it gives us a convex problem in the remaining variables, if the original one was convex. So a good example of that is a way that we can rewrite SVMs. I personally like this form a lot more than the other form. This form down here, it tends to remind me of regression, which is something that I'm kind of more familiar with in general. So we can actually, in a sense, minimize out exactly over these slack variables c. The other reason I like that is that this one doesn't force me to pronounce that. And we write the constraints, basically just combine these two constraints as lower bounds on c. That c must be bigger than or equal to 0, but also 1 minus yi times xi transpose beta plus beta 0. And we can actually argue that, indeed, we can't ever have a strict inequality at a solution. If we had a strict inequality at a solution, right, then we would be making the criterion unnecessarily large, right? Because I could always move it down to an equality. I would still be feasible, but I'd make the criterion smaller. So there's no way I could have a strict inequality at a solution. So we have to have an equality. And now we've solved actually exactly for xci. It's just going to be equal to this at the solution. Plugging that back in gives us something that we call the hinge form of SVMs. So I remember it as, it's like similar to ridge regression, except for the loss is actually the difference between 1, which is kind of what you hope to expect if you're going to multiply the label by something that tells you what sign of the boundary you're on, xi transpose beta plus beta 0. And we'll look at the positive part of that difference. It's called the hinge loss. And this is providing regularization just like ridge regression would. That's the way I remember this form. So this is equivalent to this. And in fact, this is convex just because this was. And we applied this partial optimization rule. Okay, we just minimized that over c, and we got a convex problem. I think statisticians in general tend to write it in this form. This is more common in machine learning. You'll see this much more commonly in machine learning. Okay, so continuing on with things that we can do to optimization problems, we can always transform the criterion. This one is hopefully going to be intuitive. If we have a monotone, let's say, transformation, let's say it's increasing, and we transform the criterion by that transformation. So let's say like e, like the exponential function. If we take f of x and we replace it by e to the f of x in an optimization problem, then we have not changed the solution. Okay, that should hopefully, again, just be intuitive to you that minimizing f of x and minimizing e to the f of x, because the exponential function is monotone, increasing, we're not going to be changing the solution at all. So we can often use this to reveal maybe a kind of hidden convexity to a problem. And the biggest example of this is going to be familiar to certainly the statisticians, but hopefully to everybody. It's just maximum likelihood. Right? So if I want to maximize the likelihood, I'm going to kind of abuse the way I'm writing it. If I want to maximize the likelihood function, that's equivalent to maximizing the log likelihood. Just applying a monotone transformation to the criterion. And for many things, like, for example, the Gaussian distribution, but anything that follows exponential family form as another example, so like Bernoulli or Poisson data, this thing is not going to be concave in the parameters, but this thing will. So if I maximize the log likelihood, I get a much more tractable problem. Okay, so that's hopefully a somewhat familiar example to a lot of people. So monotone transformations just work in general. We can also transform not the criterion function, but the variable itself that we're using to do optimization, but that requires a bit more conditions. Essentially, if we have some map, let's say that's a one-to-one map, and its image is all of the feasible set. So it means that I can hit any point in the feasible set by x by looking at some phi of y. Then I can actually change variables in the optimization problem from x to phi of y. Okay, so I can rewrite this as minimize over y, f of phi of y, subject to phi of y is in the set C. The biggest examples of this that we'll see are just linear transformations. They're not really anything complicated. So, okay, I'm going to skip this example of geometric programming because I think it's interesting, but we never really revisit it in the class. It's an example in which you have a non-convex problem kind of transparently, but you can turn it into a convex one by doing a bunch of transformations. So I'm just going to skip that. Do I have an example for, I don't have an example for, oh, yeah, here we do. This is my example for essentially change of variables. It's eliminating equality constraints. So it turns out generically, if we have a, let's say, a convex problem of this form, we can always re-express this as a problem without any equality constraints just by changing variables, applying that change of variables rule that I told you before. So we're going to reparameterize the set of all x that satisfy ax equals b in a particular form. We're going to say, let's just pick some x0 that satisfies ax 0 equals b. Let's let M have columns that span the null space of A. It's one too many L's. Null A. Then I can write the set of all x such that ax equals b as just the set of all, let's say, x0 plus my over all y. Okay, so basically I'm saying we can get any solution to this by just taking a solution and adding something in the null space. And if the null space only contains 0, that means there's only one solution and it's x0. So again, this is just a basic fact from linear algebra. And now that I apply this fact, I can just reparameterize this problem as to being 1 in terms of y alone. So anywhere I see x, I'm going to write that as x0 plus my. So I replace my plus x0 in the criterion. I replace my plus x0 in all the inequality constraints. And I have no more equality constraints because by design, any one of these points, my plus x0, is going to satisfy this constraint. Okay, so this is fully general. You might ask, why do we ever have equality constraints at all in the slides if we can always do this? Seems like it makes our life simpler. It's not always a good idea, practically. There's two reasons, but there's kind of one big reason why we don't do this in general in practice. Let's see if anybody can guess.
Reduces the set of possible solutions we need to optimize over by using equality constraints.
I don't see that as being a bad thing. I'm asking why we don't do this. So, yeah.
Because we need to invert edge and it can be a big matrix.
Yeah, so one is just forming this null space, forming this M, right, whose columns span the null space of A, or in other words, the columns are, let's say, a basis for the null space of A. That could be computationally difficult, especially if A was big to begin with. So M could be difficult to form. Even more so than that, M is going to be generically dense, no matter what A was. So the way we get it is that we'd open up R or Python or MATLAB, and we'd probably do the SVD on A. Unless we're more sophisticated, we'd probably do the SVD, and we'd get the basis for the null space from that. That's going to be a generically dense matrix, no matter what A was. So if we had a sparse set of equality constraints, that actually might be fantastic for us in terms of our optimization algorithms that we'll learn later in the course. That might help tremendously in solving this, having a sparse matrix A. We would kill that by rewriting it in this form. Because no matter what A was, M is going to be dense. That's essentially why you don't see this being invoked in practice as like a general rule. Because we would destroy any structure or sparsity that we had in the original matrix A in these equality constraints. I think I'm still have a few things to go. So I don't need to introduce the last example. It was only to do with something called the fantope, which was supposed to be for fun, and you'll see it in the homework anyways. But I'm going to, I mean, and not in a bad way. We'll introduce to you what it is in the homework, and you'll. That sounded bad, but you'll be fine. On the homework, it's quite an easy problem involving the fantope. I'm just going to basically introduce two things, and then I think we'll have time right before we quit. So there are two more things you can do to optimization problems I wanted to introduce. One of them is introducing slack variables into a problem. Okay, so if I ever had inequality constraints that I didn't like, we just saw how to eliminate equality constraints. If I had inequality constraints that I didn't like for some reason, then it turns out I can always essentially get rid of them and replace them by linear inequality constraints by introducing what we call slack variables. So this inequality you can see is equivalent to gi of x plus si is equal to 0 for some si that's non-negative. Right? If I force this to be true for an si that's 0 or positive, then gi must have been less than or equal to 0 to begin with. And we call these s's slack variables. This is sometimes a useful thing to do, because sometimes it's easier just to deal with linear inequality constraints. And in fact, sometimes it may just be easier to compare a slack variable to 0 than whatever we had in the first place. So we'll see this in linear programming. We often rewrite things in a form that kind of comes from this. But this will destroy, unlike our previous slide about removing equality constraints, this slide, removing inequality constraints, will destroy convexity in general unless this gi is linear. Right? Because if gi was a convex function that was nonlinear, now we've introduced an equality constraint that involves a nonlinear function in x. Okay, so we have to be very careful when we're introducing slack variables to remove inequality constraints. Basically, you should only do that if you really want to. So how would we relax? How would we deal with non-affine equality constraints? This follows from a general perspective that we take that has to do with convex relaxations of problems. Hopefully something we'll revisit towards the end of the semester. But in general, if you ever have, let's say, a problem of this form, this generic form, where this set C is potentially non-convex, I can always enlarge the constraint set by taking a C tilde that contains it. And the optimal value to the problem minimize f subject to x being in C tilde is only going to be lower than what I started with. Right? Because I'm making the feasible set larger, I can only achieve a lower value of the criterion. If C was non-convex and we enlarged it to be something convex, like it's convex hull, for example, for C tilde, then we call that a convex relaxation of the original problem. Right? Pictorially, it's something like I have minimizing f over some set like this. It's not convex, so I'm going to take its convex hull, which is the smallest convex set containing it. And if I minimize f over that, which is C tilde, then I can expect the criterion value I find at optimum to only be lower than what I would have gotten if I had looked at the original set. So this is one way that we deal with non-affine equality constraints. If we have things like hj of x being equal to 0, and these are actually convex but not linear, we don't really know how to solve those. If we actually change this to less than or equal to 0, then we've effectively enlarged the feasible set. Okay, we've made in this form, we've kind of formed a C tilde that's bigger than our original constraint set C. This is now a convex constraint, so we know how to solve it. But we potentially end up with something that's better than what we hope for in terms of the criterion value. Right? This thing is going to potentially be lower at the solution than it was originally for our original problem. So this is, again, called relaxations. And this is an example in which we do such a relaxation. We have a nonlinear equality. We relax it to a an inequality, and this is a particular example where we actually can argue that that did not change the optimal value. So if we can argue that by relaxing the optimal value, the relaxed problem is actually no better than it was originally, then we've actually we haven't changed the problem at all. So I'll have the guest lecture on Monday go through this problem because I think it's an important one to understand. Sometimes you can take a convex relaxation of nonlinear equality constraints and you can actually arrive at a convex problem that's equivalent to what you ended up with. Okay, that was it. Thank you guys for staying a few minutes over, and I won't see you on Monday, but I'll see you on Wednesday.